gets introduced. And he will talk your head off probably tonight, right? Anyway, who has been here before? We have some returning people here. We have some new faces too. Let me give you a 2-second or 2-minute overview of what we do and why we do it here. This is a little non-profit organization separate from the school, although we work very closely with the school. We started this observatory in 1997 when we got a telescope donated from Mount Wilson Observatory in Pasadena, California. And we started the Little Thompson Science Foundation for fundraising purposes and to build and run this observatory. 1998, started building it. 1999, opened it. And we have expanded it once in size. It was about half the size it is now. We put 2 domes on finally. We have 2 big telescopes. The second one that we have is an historical NASA telescope from the early 60s that was built for the NASA Apollo program to figure out if the moon was hard enough to land on the surface and to pick the landing spots for the Apollo missions. So we are almost ready with that telescope. The telescope is all set up with automated point and click control. The dome has to be automated still, so we're not quite operational yet with that historical telescope. On the other dome, we have an 18-inch Tinsley coupled with a 6-inch refractor, an astrophysics refractor that we use for all our groups and for all our viewing of the sky. Since 1999, we're past 47 or 48,000 visitors, so we hope to see our 50,000th visitor this year. And no, it's not in this group. Okay. Probably November, December, so we'll come back towards that time. And who knows, you may be the lucky one, the 50,000th visitor. Let's see what else. We run this place with all volunteers. We're always looking for new volunteers, so if you want to sign up, go to our website, starkids.org. Sign up to be a volunteer. We'll teach you how to talk to a group, to an audience, teach you how to operate the telescope. And the neat thing is, after you qualify to run the telescope, after the groups are gone, I mean, you can work with the telescope. You don't have to buy a big telescope yourself. You can basically come in here and operate the telescope yourself, so that's kind of fun. Of course, if you do that, it will make you work harder. So, so anybody who wants to sign up, go to the website or talk to one of our volunteers. We have some volunteers here. They wear these badges like Jimmy. I forgot mine. Who are you? Who are you? I don't know nobody here. So anyway, that's what we do. We were hoping for hot, clear weather tonight because for the first time in our dozen years that we've been here, we finally have a swamp cooler on the roof so we can cool this place. For those of you who have been here in past years and kind of sweated through the August evenings here, that was kind of uncomfortable, so now we have a cooler on the roof that we're trying to use right now, but it's barely needed, I think, right now. Another thing we're doing tonight is we're trying to get rid of our t-shirts. So we'll do t-shirts for half price or whatever, $5 a t-shirt if you want a blue or a white t-shirt. And these are kind of classic because the building is a single dome building, right? Right now we have 2 domes on the building, so you will never get this again.
Collector's items. There's many more down here, so it's not just what's taken up.
Yeah, we have lots of them still. So we're trying to. Beg your pardon?
Children's sizes?
We have small and small and medium, yeah. I'm not sure we have children's sizes per se, but the smallest size we have is adult small. But I think if you wash them hot enough, they'll. Right? starting to finish up on our Lakota Sioux constellation wall here, and I have just confirmed that one of the chiefs of the Oglala Sioux out of the Pine Ridge Reservation will be here in our October start to talk about the Lakota Sioux beliefs, the Lakota Sioux constellations, and some of the stories that go with that constellation wall. So I think it is the 20th or the 21st of October. Keep that in your calendar. That might be a fun evening when you get a Native American Indian talking about really about a 3,000-year-old constellation maps that have some things in common with the Greek-Roman constellations that we have on the other side of the wall, but that have a lot of very interesting new ideas, at least to us, new ideas, and they incorporate it in their everyday life. So that will be a very interesting talk. I'll try to get more chairs, but I'm sure that we won't have enough room otherwise. Okay, let me introduce John Ensworth. Yes. Oh, the Fort Collins Lighting Ordinance. I just heard about it. This gentleman in the front row.
Yeah.
I don't even know his name. My name is Mike. Your name is?
Felix.
Felix. That's a very nice name. It sounds German.
It's actually Italian.
Felice. Well, then you know how to say it. Felice.
Yes.
But maybe you want to say something. Sure, say something about the Fort Collins Lighting.
Yes, the city of Fort Collins adopted in their green building code amendments. We recently adopted one of the provisions that requires no glare lighting on new structures.
Yay!
Give the man a t-shirt.
What size? Amount to.
A large, medium, or large, I think.
Large? Yeah, sure. I work into it.
We have a winner.
All right, white or blue? Which one would you rather have?
This is
Either one.
actually
Both.
yeah, I think
Yeah.
that's true.
In 2008, Berthoud passed their lighting ordinance, their dark sky ordinance, and that was actively promoted by this observatory. And I think one of the classes, senior classes here at the high school, they wrote a lot of the research and wrote a lot of the text for us to put into the ordinance. And we're happy that all new construction in Berthoud also is now dark sky compliant, so downward lighting, low wattage if possible. If you have a chance tonight to drive through the main street in town, Mountain Avenue, from about 5th Street all the way to the roundabout, that is all the new street lighting that is dark sky compatible. Each one of those street lights is only 85 watts. Believe it or not, they replaced Cobras, which were 240 watts. Pretty glare bombs. So we like dark skies for obvious reasons, right? Anyway, let's go back to John. He's worried about that he doesn't get a chance to learn. John found us on the internet when he was in the process of moving with his wife from Greenbelt, Maryland, or Gettysburg, Maryland, to Longmont. And he found us and he said, boy, I have, I don't know how many, 50 years of scientel or 30 years of scientel in astronomy magazine.
Oh, yes.
I said, well, we have a lot of them, but we have certain years we're missing. So he said, okay, let me take those with me, and then I want to be a volunteer at your observatory. So we said, fine. What is your background? So John's background is basically in science education. He has too many degrees to even go into his resume. He has metrology, astrophysics, cosmology, math, geology, engineering, I mean, you name it, the guy has done it. Has he ever worked in his life? I don't know.
Professional students.
No students.
Yeah. But we're very happy to have him here. He is that's where the idea came from. Let's do this talk about the theory or theories of everything. Of course, it all starts with the beginning of time. That's where he's going to start. And that's why it takes 2 months for him to get through the talk. Right?
It's higher than 13.
And it gets into quantum mechanics and all that good stuff. And he promises me that even people with a 13-year-old kind of level of thinking and level of experience can understand it.
Raise
Is that right?
through it. Yep.
You're going to race through it.
Raise through it.
Yeah.
Top of the glass.
He is encouraging questions. Don't hold them till the very end because you will probably be overwhelmed with all the stuff that we're going to talk about. We're very, very happy to have him here. Ask as many questions as you want. It'll probably be an hour to 75 minutes, an hour and a half. Okay.
It's cloudy, eh?
He said he did that on purpose. He didn't want to compete with a telescope.
It's
So,
my secret meteorological powers.
any questions before I turn it over to John? Anything you ever wanted to know about the observatory? Okay, well then, John.
So we're going to go from, the beginning of time forward, and I won't dig deeply into all these different topics. If you've read Sky and Telescope, Century of America, if you've watched NOVA specials and things like that, the topic, you will have heard enough to see what we're doing here. We're basically gluing together big chunks of what astronomers and physicists are working on. And one of the big things that one's going for is the theories of everything, or a theory, one theory of everything, hopefully. Because there's some way of looking at this 10 to the 500 power theories of everything, so we don't have time to cover all those here. But we'll jump into that. So we'll go through all that. We'll play around with string theory this month, and then we'll talk about some of the problems that are arising, like dark matter, dark energy at the end. And then next month we'll get into information side of things. We'll look at entropy. We'll look at some of the interesting things coming from that. So I'll get there just a little bit. I'll start off with a good quote from Stephen Hawking, one of the pioneers working on this, saying if we do discover complete theory, it should be in time understandable and broad principle by everyone. Then we shall, all philosophers, scientists, and just ordinary people, be able to take part in the discussion of why we in the universe exists. So, we don't have the theory yet. We should be able to, as we go, make this all accessible to everyone. From Brian Greene, who's another great researcher on this, is no matter how hard you try to teach your cat general relativity, you're going to fail. Also from him, he says, we can certainly go further than cats, but why should it be that our brains are somehow so suited to the universe that our brains will be able to understand the deepest workings? And we'll explore that as we go through this month and next. Just the thought that, well, we're good at smartphones and going to but how is it that we can even understand weird things like quantum mechanics? Because that's a very strange world in there. Next month we'll talk a little bit more about the weirdness of quantum mechanics, and then sometime in the future, in the next year or so, we'll probably have a quantum mechanics for dummies talk. I'll just take the very basics and go forward with that. But it's weird stuff. It's stuff that doesn't make any sense to your everyday experience, but yet you're made up of it. So it does seem that we're wired to make sense of the world around us. Our brains like to take old ideas and link them to new, and we make categories about just about everything. That's definitely how biology got going. Was Darwin was marching around and classifying and sketching and taking pieces of things and putting them in books, and we simplify and simplify and simplify before we even have ideas linked or mechanisms behind things going. An example I like to use is if you looked outside and you saw things that are green, and I could jump ahead and say, well, there's weeds out there and there's blades of grass, but I'm not going to do that. I'm just going to say these are all green things out there covering the earth. And there's a bunch of green things floating in the ocean too, and they're very tiny. And if I didn't do this, I would have to have a name for every single one of them.
And if a leaf died, we'd have to take that off of the books. Leaf number 1,704,000,000 died. So, and it's just too much to manage. So we group things together. You could maybe say, oh, there's some things that are trees, some things that are grass and moss. That narrows it down to about 500,000 things. That's still a lot of names to learn. But you could then look at the thing that makes them green, the chlorophyll itself, and there's only 6 related kinds. So now you've simplified all these green things we see out there tremendously. And you can make predictions about how some will respond to more sunlight, some will respond to less water, without having to know, well, one leaf number 700, 400, billion, trillion, is now in full sunshine. What's going to happen? So we do that, and it serves us well, and that's what we're going to try to do with things like string theory tonight. Well, way back, before science really kind of got systematized, we had myths, and they were all-encompassing explanations that simplified the world around us, and what they really often had was breadth. They covered a lot of whys that people would ask. There were observations behind them necessarily. They didn't necessarily make predictions, but they covered a lot of things, and I guess they let people sleep at night. What we want with scientific observations and investigations is some depth. We want to look into why this happens, what are the causal effects, and what is the outcome. We need to make predictions. As a meteorologist, predictions are a big thing, and we get an awful lot of flack from you guys about the bad forecasts. All right, so creation myths are the first theories of everything that were out there, and myth nowadays sort of is morphed into the word untrue. That's not how they originally were intended at all. They were the best people could do. Often dealing with origins, of course, where we came from is a big question. And a theory of everything should at least help with that kind of question. We're wired to expect that if we're here, we came from somewhere, that there is a cause and effect. So we'll play with this, keep an eye on this as we go. So going before Copernicus, got a mind of its own. Of course, he had astrological and astronomical observations going back, even some constellations have origins going back thousands of years. Aristotle, in about the 300s BC in Greece, came up with a picture of crystalline spheres with the Earth in the center, everything going around us. The last sphere was dark, it had holes in it, the light of heaven shone through, and that was stars. And it was not really a science, but it was good enough to last for a couple thousand years. The Earth was changeable and imperfect, the heavens were not changing, except we had wandering planets and an eclipse that happens every now and then, but those exceptions. But one of the reasons that helped was there wasn't a parallax. Parallax is, you go ahead and put your finger out in front of you and close one eye. Okay, now switch eyes. See how your finger jumps back and forth? And we measure distance out in the universe that way. You're watching the stars as the Earth goes around the sun. So the nearby stars wiggle compared to the ones further back. Since they didn't see that, then spheres like this are a really good assumption. Right now, taking a quick jump ahead, just giving you an idea of where we're going, so we're going to play with these 4 forces. We got gravity, electromagnetism, strong and weak nuclear forces down inside the atom. And it would take just too much time to cover all of them, so we're really going to look at gravity. I'm going to spend all my time in this first part tonight showing how gravity came under scrutiny and got worked with. And our goal is unification of these forces, to come up with a theory that shows how these maybe were all one force in the past. So Aristotle didn't help us with gravity, didn't concern himself with that. Now, Copernicus comes along, and we've jumped a long way forward in the future, into the early 1500s, and he came up with the Geocentric Model proffered it to the suns in the center of the solar system, wrote their revolutionists, that's how you would say it, finished in 1530, and we have planetary motions now, without having to go to really extreme measures of putting secondary circles on the orbits, to explain why the planets move through the stars, make little loops every year as they go. But he still expected perfection in the heavens, like we had from Aristotle, so perfect circles were still the norm. And so he actually had to put little fudge factors in there to make these planets do what they're supposed to do. All right, so after Copernicus, we have Tycho Brahe comes along, and he made observations of the sky, but he didn't have a telescope, he just had a big long tube, and he measured 777 star positions to great accuracy, planetary positions daily for 20 years when it wasn't cloudy, and really started to come with a systematic record of what was happening in the sky that someone could work with. He wasn't good at math, so he found a young guy named Kepler and hired him to do the work for him. Kepler was very poor, but was discovered, I think by a bishop, as a mathematical genius. He had his own theory of everything that he was working on with 5 solids, and got perfect solids of a pyramid and a square and a dodecahedron and like that. And he was trying to explain planetary motions with that, and there it is up there. And of course that didn't lead him anywhere, but it was a nice attempt. Tycho died, and he ran off with all the books of data, which made Tycho's family chase him for years. He had to go into hiding. But he continued to work on it, and he figured out that ellipses were better than circles. So something less perfect up in the heavens there. He came up with the 3 laws of planetary motion. So we have now a relationship between how long it takes a planet to go around the sun and how far away from the sun it is. We can test it with Earth here. So how long is Earth year in years? Okay, 1 squared. Okay, how far are we in Earth-Sun distances? Yeah, 11. So 1 cubed equals 1 squared. Great. You got to test everything. You can't just all right, so now we jump forward in time again, and we have Isaac Newton. Now, looking at the notes that we have from Kepler, he almost came up with the law of gravitation. He was close. He had a lot of work done. He just didn't try to go forward. Why gravity was doing this, or what gravity might even be, didn't seem to cross his mind. But it did cross Isaac Newton's mind, and he was pretty darn good genius. I mean, he tried, dabbled, and made progress in many, many areas of scientific investigation. But he actually expressed the nature of gravity and had to invent a new mathematics to do it the easiest way. We were talking right beforehand about how you can express things in like one coordinate system and another, and it can become a lot simpler if you express something in a different coordinate system. So expressing motion using calculus, it's really easy. So someday I'll teach calculus here too. We won't do that tonight. If you ever played with high school physics or up, you've played with F equals ma. That was his little genius there. But there's Newton's law of gravity. So you have 2 masses, and you have the distance between them squared on the bottom. You got a constant in front of that, and now you can figure out the force there. So he now had a really good equation that tells you what gravity is going to do. And from this, you can go and get the planetary motions as you wish. This is good enough to get New Horizons mission out to Pluto. We don't have to use newer stuff that I'll mention in just a second. It is really good for everyday human lives and our level of speed and the quietness of space around us. maybe gravity is really all the forces that exist. And we have Roger Boskvich, who he had an idea gravity was the only force, which we're kind of trying to do right now. It's still one force. But when you got way out here, it acted just like Newton's law said it would. But as you get down inside the scale of molecules and atoms inside an atom, then the force becomes attractive and repulsive alternately, and that explains everything. Well, it doesn't. So that was a good first attempt. Let's take a peek at the history of these other forces that we have out there. One was electricity. That was known to the Greeks. We see record of it discussed back in 600 BC. The Chinese, 270 BC, knew of electric eels. Of course, Benjamin Franklin in the 1700s. Did he fly a kite or not? But by the best accounts I found, he probably did not do it himself. He proposed the idea, and it looks like other people did it, and at least one person lost their life doing it, because that's a dangerous thing to do. Magnetism, you can get iron ore in the ground that has natural magnetic properties. That's one of the ways that we figured out that the Atlantic is spreading apart and helped shore up, no pun intended, plate tectonics theory. And Chinese even used them in compasses at 100 AD. But it wasn't until the end of the 1800s that Maxwell came along and unified them into one theory. Now we have electromagnetism. We see that these are two aspects of the same entity. So we don't think of them as separate things anymore. If you move an electric charge around, you generate a magnetic field, and if you move a wire through a magnetic field, you get an electric flow. So two aspects of the same thing there. The word now is recent as the end of the 1800s. So you can see understanding is very recent to the human race. We have our iPhones and we think we know it all. So let's get a little historical overview here. We've got Copernicus coming in out of the 1500s towards 1550 here. We have Magellan going around the world, Michelangelo, Leonardo da Vinci, and Columbus doing their things at this time. This shaded area is called the 99 years of astronomy, where astronomy really leapt forward as a science. And this is by historians, so it's catchy. I don't know why it's not 100, but we have Galileo during this time. Here's Tycho and Kepler figuring out how planets move around. We have Shakespeare, Queen Elizabeth I, Rembrandt at the end there. Coming out of that time, we have Newton. This is where he published equation for gravity. And here's where Boskvich was trying to put things together as well in just after 1550. During the time of Benjamin Franklin, we have Bach and Mozart and Beethoven playing through these times. So I'll give you an overview here. There's George Washington coming on the scene. So let's now jump into the 1900s, and you've got Einstein. Anybody ever hear of him? Just checking. As scientists go, rock star. So basically, as a teenager, he wondered what it would look like if you tried to catch up with light. Another way to say that is if I have my little laser pointer here, and I'm hitting the Lakota wall, and obviously standing here, the light coming out of my laser is going out there at the speed of light. So we usually get that little C, as in E equals mc squared. And that's all straightforward and simple, but if I back up a little bit and then run forward, how fast is the light coming out of the laser pointer? You want to answer? Yes, very good.
How do you make it turn blue like that?
Really fast. There actually was, I guess in California, a case where a driver was pulled over for running a red light, and he went to court and he said, actually I was speeding, which was kind of severe of a thing. I was going so fast that the red light had blue shifted into the green. So taken some physics in college, and then went back into his chamber, looked up the equation, did it, said, all right, well, this is going to be a $1.2 billion speeding ticket. He went for the red light. So Einstein worked with that question, and through very simple geometry and algebra came up with the energy-mass relationship, that energy and mass are interchangeable. Just this little number, speed of light squared, goes in there. Makes it a lot of energy out of a little bit of mass. And came up with two important observations. One is, first one he came up with is special relativity. He showed that time slows and space shrinks as you go fast. So, the answer that Einstein came up with is, as I'm running along, the speed of light is, as he said, always the speed of light, no matter what speed I go. So if I'm going at the speed of light, and I turn on my laser, it's still going out at the speed of light. How can that happen? I mean, what's going on here? Well, what's going on is time is not the big, regular clicking metronome that everybody is used to in your slow little lives. I'm not insulting your life. My life is a slow life too. Time slows and space shrinks. So not only that, when my laser pointer at me start getting squished in the direction that I'm going, at the speed of light, I'm vanishingly small, very tiny. And when you do the math, you find out, well, that's why it's still leaving at the speed of light. He worked a little bit further and brought in gravity into the story, and found that the same thing happens as you get closer and closer to a big gravitational source. Time slows and space shrinks again as gravity increases. This is a warping of time and space. In fact, rather than just give us an equation for gravity like Newton did, he now gave us a mechanism for what gravity is. And that is a bending or warping of space-time itself. In space-time are these woven together entities that change together. So, I had a good thought. Okay, so yes. So with us sitting here on Earth, well, yes, question?
Seeing you run, I mean, space-time is the aerobic exercise.
It is.
Give him a t-shirt.
Oh. I like the demo. Also, if you have a question, shoot an arrow. I'll stop on a dime.
Give him a chance to drink something.
Yeah. But, so sitting down here on the surface of the Earth, gravity is bending space and time a little bit. Time is going slower. So if Einstein hadn't been born and nobody had played around with these ideas, as soon as they put up the GPS system and started selling things with GPS receivers in it, it would have worked about a day and then started being further off and further off and further off and then useless. And they would have had to come up with some little fudge factor that would have been the equations of general relativity. So it would have been discovered one way or the other, but these satellites up in orbit are going slightly faster forward in time than we are. Now, the most extreme case of this is in a black hole. When you get to an imaginary surface around the black hole, well, I know the point of view is imaginary, now the point of view is where everything is, but we'll get there later. Time stops at the event horizon. Events stop happening. There's no more inventing for anybody. So we'll hit black holes in a second too, because whenever you start playing around with the nature of reality like this, it's always good to throw it into a black hole and see what happens. It's the most extreme environment that we can come along with. So, very pivotal discussion of descriptions of reality here. Then he turned his attention to electromagnetism and general relativity, because he saw how good Maxwell did putting electricity and magnetism together. They unify. So it made sense that gravity should fit in there too. And there's other reasons involving higher dimensional stuff that gave him hints that things might be good too. But he worked on it till the day he died and did not succeed. Problem was that something else that actually he also started was the quantum revolution, description of how things happen down on the scale of an atom and below. Quantum, you're talking about quantum mechanics or quantum physics, sort of fuzzily it means what's happening in very small spaces. Quantum itself means energy comes in discrete little packets, little quanta, little bundles. But it's most noticeable at very small scales. So, help you with a definition there of what quantum is all about. And you have the TV show Quantum Leap and that. There actually are quantum leaps in atoms all the time. It's part of how atoms work. But the idea of an atom goes all the way back to the Greek philosophers, and in their definition of an atom, it was the smallest divisible unit of mass, or matter. Nothing could be broken up further down from that. That isn't true. We went plunging into atoms and then inside the stuff inside of atoms, and we're still plunging down and finding things, but atoms are first detected sort of late 1700s, 1800s. A lot of argument in scientific communities whether atoms actually were there or not. Einstein played around with Brownian motions, and you can see a macroscopic little jitter of dust particles or pollen under a microscope. These little atoms bumping around. But look how recently we weren't really sure atoms were around. Just like a century or so beyond. It's a blink of time in human history. At first they thought that the stuff inside of atoms might be sort of like a chocolate chip cookie with the dough and all those parts around like that. Then they found the nucleus of an atom in 1909. They were throwing neutrons through gold, and they would sail through like there was nothing at all. And every once in a while, bing, it would bounce off of something really dense. They figured out the percentage of time it hit something, and they could figure out the cross-section of an atom, and they found there was a very small, dense center and a lot of ghostliness around it. So the natural idea was electrons zip around this central nucleus like planets go around the sun. It's a nice unifying idea. It's not really right, but it was a great picture, and it's probably still showing up in textbooks today. In 1913, Bohr modeled the atom, and quantum physics of the atoms in 2020s started to look more like this. You have these clouds around the nucleus where an electron has some probability of being, but an electron is not really always a little hard point doing anything in particular. It doesn't know exactly where it is. It just has a chance of being in this region more than over here, or in this region up here more than over here. And so things started to look creepy pretty quickly as they were dealing with atoms. Those models over there were nice, but they weren't good enough. These other two forces, as we already talked about gravity and electromagnetism, and you're familiar with electromagnetism, the lights shining down on you or sending electromagnetic waves to you. Your skin and body is all held together by electromagnetic forces. When you're touching your arm or stepping on the wall or feeling the chair beneath you, it's just electrons repulsing. That's electromagnetism also. So other than gravity, everything you have a name for and a concept for, pretty much, is electromagnetism. That is the world that you live in, is electromagnetism. But deep inside the atom, we have these two additional forces. The weak nuclear force wasn't really figured out until the mid-60s. And this one has a number of roles inside of nuclear processes inside the atom, but the most visible effect to us that we think about daily would be radioactivity. So from cesium in old glowing faces of watches to the scary stuff happening in Japan or that happened in Chernobyl like that, we think of radiation in that way. And there's some particles that, in the way that photons of light carry electromagnetism someplace, we have two little critters called the W and Z boson. That's as deep as I'm going into that. The strong nuclear force holds together the center, the dense part of the atom, the nucleus, and that's most of what you think of as having weight. So when you step on the scale in the morning, you are weighing your nucleus. So that's just the way it is. Suspected in the 20s, even without really understanding what it was, we were able to make nuclear weapons and power plants and like that. And remember, things of positive charge, like the protons, wouldn't like to stay near each other. Light charges like to pull apart. It's like two north poles on a magnet like to repel each other. So something really strong in there has to hold that nucleus together, these little neutrons together in there. And the gluon is the force particle that's like a photon that transmits the strong nuclear force. And we didn't really have that figured out until the mid-70s. This is really recent stuff. So Einstein didn't accept the quantum physics stuff that he helped launch with things like the solution to what was called the ultraviolet catastrophe, which now we utilize in all those photovoltaic cells that we have, and light sensors and digital cameras and all that. So he only accepted about half of the known forces, and he died not being able to put this all together into one theory.
So did he ever accept quantum theory?
I think even with the Einstein-Rosen-Podolsky paradox, which is we call entanglement, and I'll talk about entanglement briefly next month. He was creating that to, again, try to poke holes in it. They're saying, no, look, if what you guys say about quantum physics is right, you could move two particles across the universe and turn this one down, and then one on the other side of the universe instantaneously goes up. That's ridiculous. And then since then we found out, nope, that's exactly what happened. So in fact, that helps hold reality together. I'm jumping ahead. So even in his jabs at quantum physics trying to tear it down, he made incredible insights that helped advance it. So,
Didn't he say, God, don't throw dice?
right. There's some argument that he really did, or something similar.
Someone else said it for him.
Right. So God doesn't play dice with the universe. And we're going to see these dice before the night is over. Yes?
Question quick.
Please.
Let's say that you're looking through the Hubble Space Telescope and you get a deep field image, and the closer you get to the speed of light, the more time slows down. So if you're looking at a piece of or a photon of light that's left a star 13 billion years ago, when it finally reaches its destination in the telescope, would it be like instantaneous for that light? Would it be, I mean...
No, it still has to do the full trip. All the way here from 13.7 billion years out. And the speed of light is still speed of light, so it still has to do that. What does change is the energy of the photon, because the universe is expanding, so it loses energy along the way. So it becomes, if it was a really hot ultraviolet photon, it's now a microwave photon, very long wavelength, low energy. So that's where the loss happens. Great question. So unification has also been successful in more than just electromagnetism. The weak nuclear force and electromagnetism were linked into the electroweak force, 1974, and that's again very recent. And this helps really put together the standard model of quantum physics, which also includes a whole zoo of particles that are out there. So, leaving gravity aside, the natural instinct then is to bring the strong nuclear force in and come up with the grand unification theory, or GUTS. So, if you're going to stay up all night drinking coffee and doing this math, you come up with weird academic stories. So the idea is that we'll link the electroweak force to the strong force, and will be another big step forward in putting everything together in one force and one theory of everything. And this is still in progress. The big superconducting collider, electromagnetism. The big collider in CERN in Switzerland, France, is now reconfigured as the Large Hadron Collider. They took out the old colliders and they put this one in. Smashes protons together. They go around the circle, opposite directions in two different beams, and they steer the two beams into each other and crash. You get very energetic impacts, creating all sorts of particles from that.
Why is it called a hadron, a large hadron?
It is large itself.
So
It's a big,
itself.
and maybe, I don't know if it's 30 miles in diameter or something like that.
It's 27.
What?
27.
27?
That's cool.
Thank you very much. And hadron is another name for class of particles like protons. They're composite particles of other particles. So very high energies in a high vacuum. There you go, 27 kilometers. Very good.
Give him a t-shirt.
Give him a t-shirt. You must have 3 or 4. And so why are we doing this? Why are we right now smashing protons together? Because if the Big Bang model is right, and we haven't really talked about the Big Bang yet, but we'll get to that shortly, then this unification not only can happen just mathematically, it happens as energy levels of these interactions go up. And that happened as you go cranking your imaginary clock back in time, back to the beginning of time at the Big Bang, you had energies that high. So the thought was, as the universe is cooling and forming, these forces were actually only 3, and then only 2, and then maybe only 1 in the beginning. So you can do it mathematically, or you can try to recreate conditions of the Big Bang, or shortly after, actually. I think to get to the level, or back to one force, the estimate we'd have to have a collider ring that goes around the edge of the galaxy. So that would take a while, multiple millions of years to let your protons go around and up to speed. Boy. At these things, you ride bicycles often around, get around inside the tunnels, and I can't imagine riding a bicycle. Fun. Wouldn't get very far. They're looking for exotic particles in here. One particle that has not yet been seen in the standard model that I just mentioned is the Higgs particle, which is in the newspapers been called the God particle. And we get very excited about our theories. These grand names. But we think this should be part of the field that gives matter its mass and momentum. So they have a narrow idea, it's predicted, of what this particle looks like, and they're pushing this collider ever higher to see if we can start getting. And there's hints maybe in the data, but it's really down in the noise, and there's nothing to be said yet. So we're not there, but give it a year or 2 or 3 or 5 or like that. And again, we're creating the conditions of the early universe where maybe these forces are seen. Yeah, right.
What exactly does unification of the forces mean? What does it mean for them to be
One
unified?
force.
But what does it actually mean for them to be one force?
If it's one force, then you've got one short equation that would then predict, hopefully, all the particles and all the physics that we have.
So one force means it's one equation will satisfy it completely.
Right.
Okay.
And if you put in these numbers, out pops gravity. If you put in different conditions, out pops electromagnetism. Rather than being separate theories and separate ideas, now they're all together in one. So, and we're going to talk about it. I have a slide coming up. One, like the theory of everything is, but excellent point. So you got the unification of forces that we hope will help us with. We're going to talk about, at the end of tonight, dark matter, so maybe we get a hint of what that could be, and other problems that we have in astrophysics. Like, we believe that matter and antimatter should have been created in the early universe at the same equal amounts. And when 2 of these touch, you get a complete conversion of gamma ray energy. Just pure gamma ray energy coming out of that. And that's where E equals mc squared really shines. It shows you all the energy that comes out. When you set off a nuclear bomb, like something made out of uranium, you're not really getting a lot of energy. It's still a pretty wasteful process. It's nothing like matter probably Afghans actually, but I'm not going to get any deeper into that. So let's take a quick overview of how we are doing putting all these things together. There's electricity, magnetism, and you think of it as light. We've got electromagnetism in the 1800s. We have radioactive decay, neutrinos, weak interaction, weak force. You have protons, neutrons, and a whole host of little critters related to the strong interaction, 1973. Earth's gravity and how the planets move give us universal gravity in late 1600s. And in the early 70s, electromagnetism and the weak are successfully unified. The electro-weak interaction. We bring in space idea of space-time curvature, and we have general relativity with Einstein. Putting together electro-weak and strong, we have what's being still refined. It's the standard model of quantum mechanics. One of the problems with this is if you want to know the mass of an electron or the strength of this boson, you have to put the numbers in yourself. You have to go and do the experiments and figure them out. This doesn't just create the numbers that we see in the textbooks for all the particles that we have. That's another thing that we would like to get out of the theory of everything. We'd like it to tell us why all these particles are the way they are, why space-time curves like it does, and like that, we hope. So I'll put those together, and that's what is missing, is the link between all that good stuff and general relativity with gravity. Looking at it from forces, we've never seen a graviton. That's the imaginary little particle that would carry gravitational force around, like photons carry electromagnetism around. We don't have a quantum gravity theory, and we're going to see in just a moment why that hurts us. And we don't have all these forces put together yet. So what is this going to be good for? Well, we hope it unifies the forces into one. We hope that it'll help us with the origin and into the universe, understanding some of those things. And it probably won't help us directly explain life on Earth. Probably won't even help less in explaining why we were here. It'll help not at all on why you had eggs and bacon. So there's definitely limits to what this everything will do. So is that it? We figure out the Higgs particle and figure out where mass comes from, and then we can link everything together. No. So it says, I'll be working on the largest and the smallest object in the universe, superclusters and neutrinos. I'd like you to handle everything in between. All right. So we have two deep problems out here facing us. It's keeping gravity from easily being folded in. So gravity is fantastically weak compared to the other four forces. Just compared to the strong force, it's a 1 followed by 40 zeros weaker. And you think, wow, I mean, if I fall down and break an arm, then gravity really sucks. So it's really strong. Sorry about that. But I always forget to bring this with me. But think of it this way. If I just had a little refrigerator magnet and put a paper clip down here and go click and pick up the paper clip, and you go, yeah, so what? I do that all the time. But no, look what just happened. This itty-bitty magnet has countered the entire mass of the Earth and its gravitational force, easily overcoming an entire planet's gravitational force. The weak little magnet? No, not weak at all. So these other forces, even the common everyday things like electromagnetism, are fantastically powerful. And that makes it really hard if you're going to try to stick them into one equation together. The other problem is general relativity and quantum mechanics don't get along. If you've ever watched The Elegant Universe by Brian Greene, okay, Nova Special, he really illustrates that well. We'll do that quickly right here. So general relativity does fantastically on the giant scale of things, talking about how the universe is, how galaxies come together, how the universe is shaped. We've wondered whether it's shaped, curved space, remember, space and time curve with gravity. So you got a universe full of planets and stars and galaxies and black holes and stuff, then it's going to have some curvature maybe. It could be positively or negatively curved. I'm not going to go really into what that means, but what we see now is that it's probably very close to flat and probably infinite. So general relativity helps us answer some questions like this on the giant scale. When you go looking back in time, this is probably one of the more significant pictures that mankind has ever created. And this is the baby picture of the universe. This is looking back at the photons that are escaping the Big Bang. Big Bang was similar to the inside of a star now at some point after it all started. In fact, hydrogen was being made into helium, and we can calculate how long that expansion took and what the ratio of hydrogen to helium would be. We look around the universe, and it is that ratio, so that's really encouraging. So just like looking at the sun, don't do that, it's bad for your eyes. You can't see below the surface. It's too hot. The photons are bouncing around, knocking into other things. The density is high enough that light doesn't fly free until the surface. You could actually fly an airplane like a few percent down through the surface of the sun, because it is not that, it's not solid, it's a gas ball there. You just have to have a lot of asbestos around your airplane. So this is like the surface of the sun for the universe, from the Big Bang. This is the last point that photons couldn't fly free. Now electrons could settle down on tabs and away the light goes, and it continually headed for us until it got to us about 13.8 billion years later. And these little modeled texture here is extremely important stuff. These are slight temperature differences from just a little bit hotter to a little bit colder. But normal, just take a bunch of gas, cram it down to a tiny point, let it expand and create a universe, you wouldn't expect it. It should be pretty nice and uniform. I'll get to inflation in a moment. So here's a quick history of the whole universe. You got the Big Bang moment, you got the point where everything is pure energy. The universe got really fast, we think. We can tell it got really fast, really large, really fast. By how uniform this temperature is from one side of the sky to the other. Then we have a period of time where the universe was dark, and the first stars started to form, the first galaxies started to form, they started to blow up, make heavier elements, and that process continued on to today, where there's enough of this heavier stuff, it's not hydrogen and helium, to make planets and people and iPhones. So, quantum mechanics is extremely successful for the tiny world. Modern technology like the semiconductors in your phones, computers, that projector, all based on the weird things that electrons can do, like going through solid walls. I'll talk about that next month. Predicts particles that weren't observed, and they went and looked for them and found them. And the last one there, the Higgs particle, we're searching for now. There's a schematic of sort of the zoo of unusual particles that we've got out there. And what's really fun about trying to put these two theories together is that you can start to explain that baby picture, that modeled appearance of hot and cold. Because when we look at galaxies around us, and these are actual plots of galaxies out from Earth, why do you think there's a big notch here? Why do we have it just two directions? Yes?
Because it takes a lot of time to examine everything in one particular direction, so you haven't looked at it in every direction.
That's true, but there's another more physical reason.
Spin.
Not spin.
Center of the galaxy.
Yeah, galaxy. Yeah, like we can't see out in the universe in the plane of our galaxy, so we have an area that's harder to make reliable measurements. So look at that stuff. That weird, kind of fluffy, chunky voids and walls and strings of galaxies along. It is kind of vaguely reminiscent of that. And we think that actually this seed the pattern of galaxies from then on. And when we start working with these two theories together, we see from the beginning of time to the time when the universe was packed densely with particles coming into existence out of this field that expanded the universe really, really fast, you have all sorts of little weird fluctuations and wiggles and random things happening in the quantum world. Remember I said electrons going around the atoms are just probably there in some place. Well, we think these little wiggles and fluctuations in the early universe are now painted across this pattern and is responsible for the galaxies across the universe. Yes?
At that point in time, in the early universe, the expansion was not constrained by the speed of light.
No. Quantum gravity and string theory. Yes, where does that information? Here, the volume universe inside is reflected completely on a surface surrounding it in a higher dimension. And there's no gravity on the surface, there is gravity on the inside. So depending on which one you're looking at, you can actually solve problems in string theory that were unsolvable by just hopping out onto the surface and doing the math here. Or things you can't solve on the surface, you can hop into the volume and solve. And so, a field of hot radiation. Matter is held together by gravity, pulls it together, held up against this pull of gravity by electromagnetism and the strong force operating in here, keeping atoms together. But as you increase weight, increase mass up into an area, you start jamming things together too much for electromagnetism to hold up anymore. Anybody heard of a neutron star? Alright, so electrons are jammed into the protons. Now you have a ball of neutrons miles in diameter. So that's great for a while. And then if you keep increasing mass, things start to crush more. You might get some quite a quark star, or some or even weird material like that. But at some point, the laws of quantum mechanics don't allow it to hold up that much stuff anymore, and it all collapses down into a point. And Einstein didn't like that very much at all, but hey, there it was in general relativity. It has to be there. So black holes became another fixture that some people got excited about investigating for Einstein's time and playing with general relativity and working on a lot of that. But here we have the rules of quantum physics are working. Remember, that's very tiny stuff, but you have the mass of an entire star bending space and time. So it all becomes a headache for the physicists. Now, another way to look at this curving of space-time is that it's down to just about breaking points. You start getting infinities, you get zeros when you don't want them out of the equation. Infinities are bad. Only hard work with infinities. So, just taking a piece of tabletop and magnifying, you start to see these quantum fluctuations show up, and then space and time and like that just go wacky down in there. And when you start trying to get gravity and general relativity to work inside an atom like that, you get just a bizarre mess. And you can't solve their equations here. All right, so here we go to our first great theory of everything that tries to wrestle these two extremely successful theories into one. Superstring theory was, in a sense, shortened to string theory. You get the four forces, the three families of four particles each, and remember the forces each have a particle, like a gluon and a photon and those bosons and gravitons, whether we see them or not someday. There was not a physics graduate student who hasn't done some little cartoon involving bosons and bosons. So that's another thing you just have to do when you're a grad student. But none of them are funny either. But the idea in string theory is the way you make your attempt at unifying them is you go all the way down to the particles that no longer divide, and you go way down in scale below those particles, like an electron and a photon, and graviton, and gluons, and so forth. And you find little bundles of wrapped up dimensions and vibrating with a given energy. So now you have a unifying idea. You don't have an equation yet, you have an idea. Rather than all these creatures being their own separate critter, you have these little strings that are vibrating with a note of some kind. Some aspect of how they vibrate creates a photon versus an electron. It's a neat idea, and it actually sprang, I'm not going into the historical detail, but it sprang out of Susskind, who was playing with equations and saw what looked like an equation for strings in there. And so he built upon that, and it's gone through big up and downs and looking like it's working and looking like it's not going to work. And oh, it looks like it doesn't work. But we're going to play a little bit with string theory. So all these particles and all these forces that we've seen are doing their own thing, being their own separate creature, maybe are now strings. But the equations don't work in just three-dimensional space and fourth dimension with time added in. You need more room. You need more dimensions. And after much playing around and sometimes a 27-dimensional model considered, all sorts of stuff, it settled down to 10 being needed. You have 3 in space one time and 6 that are curled up really tiny doing all this string action down at the very bottom scale of reality. And these are curled up in special ways. Calabi and Ya, is that right? Ya. We're playing with the idea of a Mobius strip. Anybody know what a Mobius strip is? Yeah, take a piece of paper. I always forget to have a piece of paper. Does anybody have a sheet of paper? I can rip. Okay. Take a strip of paper. And you look at it, and it's got 2 sides. Great, and there's 2 sides. And we're going to pretend that it doesn't have any thickness at all. It's pretty close to no thickness. And so if I go draw it along here, my finger, pencil falls off the edge. I have to turn it over to do more work on the other side. If you give it a twist and connect it to itself, you now have a Mobius strip. So if I start drawing here and drawing, I don't pick up my pencil, I suddenly end up right back where I was without ever picking up my pencil. I've curved a 2-dimensional piece of paper into the 3rd dimension, and now I've gotten rid of a surface. Instead of having 2 sides of my paper, I just have 1 side of my paper. It's really cool. And if you get these and you cut them in half or cut them in thirds, all sorts of wild things happen. So you should do that. What they were asking was, well, what if I had a 5-dimensional piece of paper and I curled it into the 6th dimension to get a 4-dimensional surface, and they were just doing the math for the fun of it, and they figured out the mathematics of it, and the string folks stumbled on that and said, hey, these have the properties we want of these little curled up dimensions. And the vibrations can happen in different dimensions in these shapes. And so maybe if it wiggles this way, it reacts with the gravitational field. If it goes this way, it's an electromagnetic field. And if it has both, then it's a particle that interacts with both of those forces, and on like that. And when you play with the math and zoom down, rather than that crazy foamy space-time down there, you now have these nice quiet little rings or strings that calm the craziness. So it allows you to merge the 2 most successful theories in physics together. When you have particles bouncing off each other, instead of coming together in some little violent point where you can get zeros and infinities again, you now get gentle mergings and cool stuff like that. Now, pretty quickly, 5 major theories emerged, variations, flavors of string theory. some with loops, some with closed or open loops and things like that. And everyone's beginning to stress. I mean, if you have the theory of everything, you shouldn't have 5 of them, right? Along came Edward Whitten, who proposed what's now been nicknamed M theory, which might be the W and Whitten upside down for him. He added one more dimension and showed how a whole bunch of the math now simplifies. And that one theory here is actually the low energy version of this, and this is the high energy version of this, and like that. So he unified the unified theories. very, very nice. But the mathematics is colossally difficult. And some feel that it may be decades or even a century before we even have the mathematics that we need to start to come down to one single theory. There's, as I said earlier, maybe 10 to the 500 of these shapes. These shapes that we can explore. That's a lot of work. There's got to be some way, no one's figured it out yet, to start eliminating a lot of these shapes that don't create a universe like ours. So, in more recent developments of string theory, we've now really left string somewhat. We've now gone to membranes, 2-dimensional and 3-dimensional, 4-dimensional, 5-dimensional regions that interact. Of course, you can do any number of dimensions you want, so P is the variable for that. That makes these P brains. That's another physics late night coffee symptom. So we might be in a 4-dimensional universe, free of space, one of a time, separated in some 5-dimensional space from another 4-dimensional universe, and we might even have interactions with these other particles, with these other universes. So you start playing around with parallel universes at this point. I recommend Brian Greene's book, this is his latest, called The Hidden Reality, that talks about at least 7 ways that parallel universes are now popping out of, whether they want to or not, out of the physics investigations that science is heading for right now. So these other dimensions do allow these parallel universes to come about. There's a number of different kinds of parallel universes. I said that the universe is flat and infinite. Well, if it's infinite, then you've got a lot of space to deal with. Infinity is plenty of space. In fact, there's a bubble around us, about 42 billion light years inside of radius, that is all that we'll ever be able to observe currently. In fact, after this, it continues to shrink as the universe speeds up its expansion. And if you have a volume of stuff, you can calculate how many points are in it, and how many places you can put each electron, or fill it all with electrons, or fill it all with protons, or fill it all with nothing, or every single combination between, and you eventually will run out of combinations. So at some distance away, the combinations start over. So 10 to the 10 to the 122 meters away from you, if this is true, there has to be another universe in which all of you are sitting in this classroom. Another way that you can get parallel universes when you have all these dimensions to deal with is one in which new universes keep butting off. Every time a decision is made of any kind, roll a dice, and you create 6 universes as soon as it settles down. Of course, you probably wrote the universe where it caught fire, and the universe where it fell off the table and broke, or things like that, so maybe even more than 6. But you say, well, that's really silly. Where would you get all these universes, and what evidence could there be that these universes could ever exist? Well, one way is looking at doing quantum physics problems. And Feynman, in the 50s, found that if you add up all the different paths that a particle could take as it goes from here to there doing things, it really simplifies and gives you a great answer. And so, in this way, when these little photons go off to make a decision and do something, then all the other possibilities are happening in the universes right next to us. And so, a very famous and very simple experiment, we did this in undergraduate physics, was put coherent light through a couple slits and see what happens. Well, you'd expect, a couple slits, you get a couple bright spots on the other side, but you don't. You actually get an interference pattern. The light acts like waves going through, and where the waves cross, you get a bright spot. Where the troughs cross, you get a dark spot. So that's great. Light is a particle and a wave at the same time. That's nice. But what if you only let one photon go through an hour? Okay, and maybe 2 spots of light on the wall? No. Yeah, you get the same pattern. It's just as if the photon really did go through both slits and do the full wave interference pattern. So a way to look at that is this parallel universe here, right next to us. The photon did do all those other things, and it interfered with itself across the barrier between universes. So we'll talk about that more next time. I'll get into how weird the quantum world seems to be. Another use for these parallel universes is to explain why gravity is so fantastically weak. That it may be the only particle, the graviton, that can leave our universe. Spends some of its time off elsewhere. So it wastes its energy in either maybe a parallel universe or just in a higher space beyond the 3 that we see with 4 of time. Alright, so as we're playing with parallel universes, this brings us to another way to create a Big Bang. Rather than smashing everything down into one spot, you can have the universes drift towards each other, touch, bang, the universe fills with energy, and then stars and galaxies form again. And they stay apart as long as things are kind of crowded, but as the stars and galaxies drift apart, since the universe is empty enough, they drift together again, and bang, you start the process over again. Giving you a repeated Big Bang cycle and a fresh start in the universe without having to have a big crunch and things like that. So these are things almost being forced into people's consideration as they play with that. Alright, so this is all great. We've gone through just about everything here. We've talked about the universe from beginning to end. But is any of this proven? You know, we need experiments to do that. And these things are happening down at incredibly small sizes called the Planck scale, 10 to the minus 35 liters. Planck time, 10 to the minus 44 seconds. We don't have a way to probe and view strings, not directly. And we can't even think of a time in centuries to come that we probably would be able to test these things directly. So the best we can hope for is come up with some side predictions and see if they're coming true. Supersymmetry is one possibility. Every particle that we've talked about has a heavier counterparticle. And maybe we'll see a hint of this at the Large Hadron Collider. They have already ruled out some of these though. They've looked at these energies in our particles. So that's already getting a little strike against it, but it's not completely out of the game. Maybe with extra dimensions, we could see gravity if it's leaking away into other dimensions. Maybe if you get down to a scale below the separation between the parallel universes, gravity won't leak away as easily, or at all, and gravity will get stronger than it should be. So experiments are going on to look at gravity in very small spaces. It relates to the black holes at the Large Hadron Collider, because these could pop into existence if gravity is stronger than it should be, we expect it to be, using Einstein's general relativity. But we have not seen black holes either forming at the energies so far probed. So gravitational waves, just like electromagnetic waves from photons, if you have gravitons making big gravitational waves, we can see some of those happening. They might stretch strings out and let us see some of those effects. We haven't detected one yet. And we might see some of these in that cosmic microwave radiation signature. So we're looking at that with satellites. So people are looking at all these things, trying to prove it, but string theory has not yet been proven, and there's a lot of other problems to work with. String theory assumes a smooth space. It doesn't create space in itself. Space and time might come in tiny chunks. We'll talk about that next month. And then we have new challenges. That we have a universe that is presently just a little bit of normal stuff that we're made of in this room. There's this weird stuff called dark matter, makes up a quarter of the universe, and almost 2/3 of the universe, 3/4 of the universe is something called dark energy. So let's take a quick look at those before we finish tonight. Dark matter, maybe some particles we have not yet predicted or detected. We're trying to, and there's some fights out there right now that some people think they may have seen a hint of it. Others think they're nutty with their equipment. But it doesn't interact with matter via electromagnetism. So we can shine lights on it all we want. We can look at galaxy lights from across the universe and supernova going off through the universe, and it doesn't scatter it, it doesn't absorb it. It does do something to it, but it doesn't reflect it like that. When we look at a galaxy like ours, the dark matter halo around it is 10 times the size, radius of the galaxy. It's huge. We can see what dark matter does by looking at very distant galaxies and see it bending light. Einstein predicted this, and we have now seen light bending through curved space-time like large lenses. So we know that there's this stuff out there, we just don't know what it's made of. And string theory ought to handle that, or a theory of everything ought to do that. Dark energy is the bulk of the energy of the universe, just discovered in the late 90s, looking at supernova. And it seems to be an anti-gravity force. It's a repulsive force. It's speeding up the expanding universe, accelerating its expansion. Is it a new force? Is it a field that permeates all of space, which is called a cosmological constant? Is it wrapped into space-time itself so that maybe general relativity needs another add-on to it to explain why things expand in the emptiest parts, space faster and faster and faster? We just don't know. But it's very embarrassing when you can't explain 95% of the universe around you. Kind of makes you, well, it's job security for years to come. So with dark energy, we see early on, the universe inflated really fast, became fantastically large. That slowed down. Matter was close enough that gravity continued to hold the universe together, so things just normally expanded. And without dark energy, maybe it would have started to collapse back. Probably not. We don't have actually enough energy, but that was one of the candidates for what the future of the universe would be. It would be a big crunch. But now, as matter spreads apart, dark energy is beginning to dominate again, and it's going to accelerate the universe, spreading it ever further apart. So originally the thought was that the universe accelerating, this acceleration will continue, no matter what block of space and what period of time you have, the acceleration is the same. So maybe the universe would be torn apart by this in the future. Galaxies would be pulled apart. Newest observations in 2008 said, no, maybe it'll actually kind of calm down and galaxies will pull together. That would leave our galaxy alone in the big void of darkness. Everything else pulled far away. So very, very future astronomers wouldn't see a cosmic microwave radiation. They wouldn't see other galaxies. They would actually have a picture of the universe as we did about 1910. We had one galaxy with fuzzy things around it. But even more recently, in 2010, they think, okay, maybe it will get torn apart after all. So we're still working with what that'll be. So what will happen in the end? Things continue to rip apart or just keep expanding or crunch. Probably not crunch. Unless something takes this dark energy and flips its sign and has it start pulling again. We just don't know. We don't know what it is yet. So our final side trip would be another way to end time. It would be an effort to try to recast general relativity. Was to redrive it so it doesn't even have time in it. And they were successful in doing this mathematically. What they say is time is actually an illusion in this case. And each instant is like a frame on a reel of film. So when you want to see past and future, you just hold it up in front of you and you can look and see everything and like that. So time only matters when you hit play. What is the play button? What's the arrow of time? It might be something called entropy, and that's where we will go next month. I'll play around with information being more fundamental than energy and matter. We'll play with ones and zeros in the universe as being what actually makes up reality. With information theory, quantum gravity, also called loop quantum gravity, we'll talk about why time ticks forward. All these equations in quantum physics and general relativity, you can flip time, positive, negative, and everything still happens. So why does it go one direction? We'll play around with that. And then we'll bring in Gödel's incompleteness theorem, and Turing, who helped start the computer world on its way. And the way he says it, maybe there is no ultimate. Maybe you just can keep finding a cause after a cause after a cause on any system that's built on something as complex as algebra. So, all right, there you go. There's part one for you. Questions?
In general, most of the equations that govern everything on our day-to-day scale, very elegant.
Right.
F equals ma, e equals mc squared. Very elegant, first order, kind of equations. When we're trying to force, this is going to turn into a political question.
Right.
When we're trying to force the information to fit the theory, like string theory or M theory, and we start tearing into multiple dimensions, are we really describing our universe, or are we trying to fit our universe into the math that we have?
Absolutely. There is a whole branch of almost philosophy of science that talks about the application of mathematics into physics. And like the Kawhi-Yar shapes I showed, those were just figured out for the fun of mathematics. Then they were found a possible application of physics. So the thought is all of mathematics, does it exist physically somehow? And in that case, then this universe is infinitely complex. We'll just keep finding deeper and deeper and more things to play with, because there's just an awful lot of math out there. As we'll see, Gödel's theorem says it never ends.
Fractal.
Yeah, fractal's a good picture. Yeah, just you keep going down. I think you got the picture, and you zoom in and you get more. But the fact that all the way back to Aristotle, he had an idea of perfection, of spheres and crystalline spheres that go in circles and no other odd shape and like that. That we are definitely driven. In this case, when you don't have any experimental results to help push you further, we're driven by the elegance of the math. And in fact, the Nova Special and the book that he wrote that it was based on is called The Elegant Universe. And he marvels often at why this elegance seems to work, why it doesn't get messy. Why even assume that there could be a simple equation that describes everything. It's a big assumption. But so far it has led us to fertile ground. And we keep finding interesting and applicable discoveries along the way, so we're kind of bolstered forward by that. We don't know if there's an end, or whether this stuff will ever apply. Or it's almost an act of faith marching forward. Is that what you're asking?
Yeah, basically.
All right. Yes?
If we were in one of those parallel universes, you said there'd be a meeting like this, if in that meeting, instead of you're coming here because you found this place on the internet, someone called you and told you about that, would they receive a t-shirt?
I guess yes.
Thank you.
Technically, 2 shirts.
We're all out.
All out.
If gravity is
is so fantastically weak, why don't we see the strong force and other forces affect other subatomic forces showing up outside of an atomic scale?
I missed the first part. Say it again.
So, since gravity is so incredibly weak, why don't we see the subatomic forces like the strong force and the weak force manifesting themselves outside of the realms of the atom?
They both decay very rapidly with distance. Gravity and electromagnetism are 1 over r squared. The strong force is, what is it, over the 4th? R to the 4th power? Or 5th? Something like that.
It's been too long since I did it.
I know. But yeah, they decay so rapidly out that they are confined into that scale. So, carry a proton away and it's still confined to that tiny, tiny distance there. So it's actually, most of the mass of the proton itself just comes from the binding force, the quarks inside, and the strong force comes from those quarks. So they don't like to come out at all. I think they may have seen a hint of a naked quark, but the theory right now says you really can't get them out by themselves. They don't exist by themselves. So it's just really tightly confined. Does that answer your question? Yeah.
I have a question about the parallel universe theory.
Okay.
So suppose I was coming here tonight and I decided to take I-25 instead of Eisenhower out of town.
Right.
And there was a car wreck on I-25 and I died within a parallel universe. Would this parallel universe cease to exist just because I was pulled out of the equation?
If you stick to those parallel universe ideas, no. Yours is just the one where that happened. There'd be another one where that didn't happen. Right? Both the dice rolling one or the infinite size one, all those have happened. Every single possibility in an infinite universe is and has happened. So it does weird things with your mind. But the ground-basing truth on that is we'll never get to those. We don't have access to them. We can't get information from them. They can't communicate to us. There's no transfer of knowledge in any capacity from them. So you are still just you in this universe. That's it. So.
Is that kind of the grandfather paradox, where even though you may have gone back and killed your grandfather, in the reality that you live in now, that it never happened?
Right, and that all depends on which type of causality and parallel universe you want to play with. If you've got one in which you get to rewrite stuff, then you get into a paradox. But in the dice rolling one or something, you get another universe that buds off of which you've actually hopped over and you've now done this, and you may go forward and there's no grandfather, but you're still there because your history actually goes out to another universe. So you have a new world line that spirals through other parallel universes doing whatever wacky or nefarious things you're going to do. So.
That wasn't really my question. That they had around a certain, they're doing they have 4 different laboratories where they're doing.
Oh, around the ring?
Yeah.
Yeah, there's different experiments.
What each of those, can you just basically touch on what physics are they working on in each of those locations?
It's deeper than I can do right now.
Okay.
I would have to go bone up on that and read that. Yeah.
Next month, right?
Next month.
Basically, all of them are looking for the same, they just use different instruments.
Okay. So one's like a camera,
Yeah,
where they're trying to trace particles.
it's a different technology, but you just try to trace particles from the collisions. You use different technologies to look at them. The other thing that you do is the physicist that is working on one experiment, it is not working and does not have access to what is happening on the other one. So then if you find out that all the different experiments find the same result, then you feel pretty confident.
Okay.
If you find different results, it's like, no guys, go back to it.
It worked, yeah.
It worked.
Okay.
Pretty smart way to do it. Thank you. He's a shirt too. Yes.
Okay, so with these parallel universe theories, is there any particular version of the theory which would say that in one universe, a theory of everything that would explain everything would work, and in another universe, the same theory wouldn't work? Or
Yes. Yeah. And in the second one that I showed, you get other budding universes that have a complete different tweaking of all the fundamental forces. And so you have some which, if the electromagnetic force is stronger, then atoms always collapse. And so you have nothing but neutrons sitting around. You don't get stars, you don't get stellar fusion, you don't get planets forming, you don't get any of that stuff. You just have a universe of neutrons. So yeah, there's definitely little tweaks can change a lot. We'll mention next month, touch on the anthropic principle, that here we are, looking around at all this stuff, and everything is just really right for us to be here, looking around at all this stuff. And a way to play with that is to say, well, it has to be that way, or we wouldn't be here to see this stuff. So we wouldn't be talking about it if it wasn't right. And so that playing with that idea, but not spreading material out so fast that life couldn't form. And I think that was Penrose who did that, I'm not sure. But, and then we found it 10 years after that paper was published. So that reasoning actually was fruitful. So, but it also, to many physicists, that's not science. You're not making any great discoveries by saying it's special because we're here, it's special. So, did that answer your question? Or diverge?
Well, I just like to know also though, like in these like other theories or other universes, if you change the constants, that would invalidate a theory of everything. So a theory of everything wouldn't explain why a change in constant would result in certain